On the previous episode, we trained a simple neural network to predict values of the sine function. Give it x, and it will give us sine of x. We converted that model to a TensorFlow Lite model, and then generated some bytecode that represents the model, which will load into our Arduino code. If you head to the Getting Started with TensorFlow Lite for Microcontrollers page, you can see that, as of right now, only a few platforms are supported. I hope to see more in the future, but instead of trying to create our own port, we're going to try out the Arduino Nano 33BLE Sense board. Using Arduino means we can get pre-compiled versions of the TensorFlow Lite libraries. To show how we can connect hardware to machine learning, I'm going to fade this LED on and off in a sinusoidal pattern. So I'll connect it up to pin 2 and through a 100 ohm limiting resistor back to ground. In a new Arduino sketch, open the library manager and search for TensorFlow. Install the latest version of the TensorFlow Lite library, which is 1.15 alpha for me. To begin, we'll want to make sure that we can load the model, allocate the necessary buffers, which are formatted as tensors, and run inference on some dummy data. We first need to load the model, so save your sketch and give it a memorable name. This will automatically put the sketch into a folder with the same name. So go find the .h file with our model byte array that we created and downloaded in the last episode. Copy that file and paste it into the sketch directory next to the .ino file. To see the file, we'll need to close the sketch and reopen it. When you do, you should see the model.h file appear in a new tab in Arduino. Back in our main sketch, we'll need to import some libraries, but first I want to make sure that Pete Warden and the TensorFlow Lite team get all the credit for creating this example. For this sketch, we'll need to import the main TensorFlow Lite header along with several specific functions. Micro-ops contain the operations we want to use from within TensorFlow Lite. The error reporter is crucial for helping us debug errors, as it will spit them out over serial for this Arduino implementation. The interpreter is what runs the inference engine, and the op resolver allows us to register specific TensorFlow Lite operations. After that, we'll want to import our model file. I know that the definition is supposed to be in a .c file with the declaration in the .h file, but I'm lazy, so I just put it all in a .h file. Next, we'll create a debug flag that we can use to enable printing out various metrics from the inference engine. Then we set some parameters. Note that constant expression is a C++ term that lets us define constants and use them to calculate other constants. It has other uses, but that's what we're doing with it here. We put the LED on pin 2, and I'm going to estimate pi here. There are other ways to get pi in C, but I'm going to be explicit with this one. We can set the frequency of our sine wave, and we'll use that value to calculate its period in microseconds. You probably don't need this anonymous namespace here, but you'll find it used in other TensorFlow Lite examples, as they have many other files that are loaded in to test functionality. This namespace keeps these pointers and variables unique to this file. You'll notice that we define a few pointers to use later. Additionally, we set aside a chunk of memory known as an arena. TensorFlow Lite uses this to perform its calculations and store the input and output buffers. The problem is that you have to guess its size, so I'll start with 1 kilobyte. We'll compile, and if there are any issues allocating space later in the code, I can come back and increase the arena size. In setup, we'll want to wait for the serial port to connect if we're using the debug flag. You'll want to do this during the testing phase for the Nano 33BLE, otherwise you might miss serial data in the setup function. Next, we'll create an instance of the micro error reporter. This will handle sending out any problems we may encounter to the serial port. Notice that we didn't set up the serial port. I found that this happens for us somewhere in the background. Next, we have TensorFlow Lite read in our model from the sine model.h file and give us a handle. We'll want to check that the flat buffer version in the model matches what TensorFlow Lite can handle. To help keep the code size small, we'll only load the TensorFlow Lite operations that we need. If you take a look in the microops.h file, you can see the available operations. This is where using Netron can help again. Look at each layer name to get an idea of the operations needed. It looks like we have 3 fully connected layers. That means we'll need to use the fully connected operation in our code. So we create a micromutable op resolver object and call the add built-in function. In this, we tell it we want to use the fully connected operator and then register that operation. The last 2 parameters are the desired minimum and maximum version numbers. From what I can tell, operations are between versions 1 and 3 for TensorFlow Lite 1.15, so I'll set the minimum version to 1 and maximum version to 3. Sometimes you'll need to specify a specific version of an operation for it to work correctly. So keep an eye on your compiler errors and serial debugging output. Next, we create a microinterpreter object and pass it our model, operations, arena, arena size, and error reporter. This is the interpreter that will run inference for us. After that, we tell the interpreter to set aside a chunk of memory for the arena. We'll have it give us an error on the serial port if this operation fails because we didn't make the arena big enough. Then, we create some handles for the input and output buffers. If you head to the common.h file in the TensorFlow Lite source code, you can see the supported tensor data types. Because our model expects an input type of float, we should see this type being listed as 1. Before I print this out, I need to enable the debug flag at the beginning of the program. It's a good idea to check the inputs to your model by printing them out somehow. We'll look at the number of dimensions and number of elements in each dimension for the input tensor. We'll also look at the data type expected for that tensor. And now for the moment of truth. Will it compile? It looks like I forgot to make the register op a function, so I'll add some parentheses. And on this next time, I didn't define the tensor arena correctly. Looks like it needs to be an unsigned 8-bit integer instead of a signed one. Sometimes the program has trouble uploading to the Nano, so I double press the Nano's reset button to put it into bootloader mode. This re-enumerates the Nano on a different COM port, so I'll change it here. Once it uploads successfully, let's open the serial monitor. This looks like a weird error, but it's telling me that allocate tensors failed. Many times, that means the arena size isn't big enough, so let's try changing it to 5 kilobytes, and it looks like it worked this time. You should play with the arena size to get something that's just big enough to work for your application. We see that there are 2 dimensions for the input, but there's only 1 element in each of the dimensions, meaning it's really just a scalar input, 1 number. The input type is listed as 1, which we can verify that it's expecting a 32-bit float. In loop, we'll measure how long inference takes, but only if we set the debug flag. Let's try doing inference with just 1 number as a test. In this case, we'll predict the sign of 1.2, which we should expect to be around 0.93. Then, we just copy that value to the input tensor. Because the tensor is only 1 element, we just copy x to the first element. Then the magic happens. We call the invoke function and check to make sure we don't get any errors. Note that it's a blocking function. When it's done, the output value will be in the tensor buffer associated with the output handle. For now, we'll just print the value to make sure it looks reasonable. We'll also want to time how long inference takes. This can be very important when designing something that needs to act on data very quickly or work with lots of streaming data. Finally, we'll add a delay of 1 second to give us time to read the output. When we upload this, we see that the model is predicting 0.99 for the output value. That looks a little off, but should be close enough as this model isn't a great representation of the sine function. If we swap the input for pi, we can see that the output is close to 0, so this should be good enough. Notice that it generally takes a little less than a millisecond to copy data over and complete the inference function. As your model size grows, expect inference to take longer and use more memory. Now, let's do something with this model. First, we'll disable the debugging flag so that our model won't measure inference time or give us input information. We'll get a current timestamp in microseconds and transform it into a number between 0 and the sine wave period, which we do with the modulo operator. We then cast this back into a float and convert it to radians before copying it to the input buffer. Once inference is done, we use the output value to control the pulse width modulation brightness of our connected LED. We'll also print the value to the serial monitor so we can look at the plot of the sine wave. Finally, we'll get rid of that delay so all this happens as fast as possible. Once it's done uploading, we can peek at the serial output to see that it's creating a sine wave at about 100 Hz. Now, let's try changing the frequency to something we can more easily see on the LED, say 0.5 Hz. In the serial monitor and plotter, we can see that the sine wave is being generated at a much lower frequency. And the LED slowly pulses on and off in something that approximates a sine wave. Well, that was a pretty ridiculous, roundabout, Rube Goldberg way of generating a sine wave, but I hope this gives you a starting point for creating your own model in TensorFlow and then loading that model onto a microcontroller. A link to the code can be found in the description, and don't forget to subscribe if you want to see more videos like this. Happy hacking!